in the XYZ space, if we start at a point and move distance or through displacement delta y in the y direction, then the value of the function represented for our initial point as this altitude is going to change accordingly along a line that has a slope of Fy calculated at that point. That means that the change in the function in this direction is going to be what? Well, if this is delta y, then the change here is Fy delta y, so that a vector representing the change from here to here, this vector has to be j times delta y plus k times Fy delta y. So this implies a displacement vector, careful here, delta yj plus Fy delta y k. Similarly, a delta x will imply a change in this direction and let's be careful that everything I've done here applies to this vector. Over here I'm going to do this vector. The slope now is Fx, and by a completely analogous argument, this implies displacement vector Fx, and I keep wanting to write Fx here when I mean delta x, so let's just kind of obliterate that. The displacement vector is delta x I plus Fx delta x k, and that's going to be our displacement vector here. That gives us a picture of the region that lies above this rectangular region in the plane, and with my labeling and so forth I can't really shade in this region, but we understand that the region on the surface up here that corresponds to this region of the plane lies at some angle with this region of the plane. That is, its normal vector lies at some angle with the normal vector here, and it's a rectangular region bounded by these two vectors. So we can make the statement that the region of the surface above our delta A equals delta X delta Y region of the XY plane is an approximate rectangle bounded by the vectors, or defined by the vectors delta yj plus Fy delta y k and delta xi plus Fx delta x k. The only thing that could possibly be questioned here is that this is a rectangle, and I think it isn't. I think my previous argument falls flat on its face at this point. I said previously that since this vector is in a plane parallel to the xz plane and this vector in a plane parallel to the yz plane, that this must be a right angle between these two vectors, and that's clearly not so. This vector can be as close to the k vector as we wish, and so can this vector. If they can both be very close to the k vector, which will be the case if the fy and fx are both very large, then clearly they don't make a right angle, and that's the flaw in my previous argument. The region will be a parallelogram, so I can work in the word parallelogram here. Not sure I got it all on the paper, but this region here should be a parallelogram, and my assumption in the previous that this is rectangular is incorrect. It's not rectangular. So the area of this region is still easily calculated, and actually more easily than what I did in my previous erroneous attempt. We simply take the cross product, because the area of a parallelogram is the cross product of the vectors along two sides. So the magnitude of the cross product. So the area of the parallelogram not sure I can make that any better. Area of the parallelogram, exclamation point, is the cross product of these two vectors. The vectors are delta y I plus fy delta y k cross, and that's delta yj, delta x I plus fx delta x k. Let's move this over just a little bit. And it's the magnitude of this cross product, which is then the magnitude of cross product delta y crossed with delta xi, delta yj crossed with delta xi, y cross I is negative delta y delta x. The j cross I is negative k. And j cross k is I. So we're going to have delta y times fx delta x I, fy delta yk crossed with delta xi, k cross I is j, so that's going to be plus fy delta y delta x j. The magnitude of this vector, we have I, j, and k components. So it's clear that the magnitude of the vector is going to be the square root of delta y delta x quantity squared plus fx delta y delta x quantity squared plus fy delta y delta x quantity squared. And squaring everything, we can factor out the delta y delta x. And what's left inside is 1 plus fx squared plus fy squared. We can compare that with my previous expression based on the assumption that the region was rectangular, the debunked assumption that the region is rectangular. The expression came out the same except for this fx squared, fy squared. And that's the error that results from assuming that the region is rectangular. The region is not rectangular. Its area is given by the magnitude of the cross product of the two defining vectors. We conclude with this statement then that the area, which we'll call delta S, on our surface corresponding to area delta A in the xy plane is square root of 1 plus fx squared plus fy squared delta A. Delta y, delta x being the area of this region in the plane. And with the important qualification that fx and fy are evaluated at a point in that plane region in the delta A region. Now that's kind of a vernacular statement. We can make it more precise. Your textbook will make it more precise. But stated in these terms, we're going to be able to apply it now when we subdivide an interval by partitioning the x and y intervals or the r and theta intervals. It really doesn't matter which intervals we partition, as long as we get a fine partition, and delta A represents the area of, let's say, the ij element of a partition, so that delta S ij would be the surface area corresponding to that plane area of our partition. In that context, we understand that fx and fy are going to be evaluated at a sample point in the region defined by our partition.